This is a problem about average normal stress and average shear stress. The plastic block is subjected to an axial compressive force of 600 newtons. Assuming that the caps at the top and bottom distribute the load uniformly throughout the block, determine the average normal and average shear stress acting along section AA. So what we're doing here is we're making a sort of method of sections cut along AA, and we want to know what's happening with the internal forces there and the stresses that those internal forces produce. Let's develop an approach on how we might do this. It seems that there will be two steps to this. The first one is we have to find what the internal forces are. The second one is we have to figure out how those internal forces produce normal stress and shear stress. So step one is to do a method of sections. At section AA. And the goal of doing this is to develop an understanding of what the normal load and the shear load are at that section, because those are the force components that are going to give us the average normal and average shear stress. Then the second thing is we're going to make the average stress calculations. Now in this step, one thing we're going to have to do is calculate an area on which to base our stress calculations. And as you'll see, it's just based on the geometry of the method of sections cut. Let's go ahead and get started. Part 1, method of sections at AA. Let me go ahead and make a sort of a 3D drawing of what the method of sections cut looks like. Here is our 3D section. We've got this 600 Newton load applied at the bottom. And up here I'm going to identify the centroid of the cross section, and through that centroid I'm going to draw two force components. One is the shear force V, which is acting in the plane of the cut. One is the normal force N, which is acting perpendicular to that plane. And if we put a coordinate system here, say X and Y, we can measure the angular orientations of these forces by knowing that the problem statement told us that this is 30 degrees. Okay, so if we go ahead and have a look at this part right here, we're going to find out that the shear force is oriented at 30 degrees and the normal force is oriented at 60 degrees from the negative x-axis. So the geometry here isn't all that difficult. Now what we have to do is use equilibrium concepts to go and figure out what N and V are. And that's reasonably straightforward. You can see that both N and V are going to have both X and Y components, and so we have to do the projection onto the X and Y axes. So for example, if we did a sum of the forces in the X direction, we would get V times a cosine of 30 minus N times the cosine of 60 equal to 0, because there's no externally applied load in the X direction. And we'd end up with V is equal to N tan of 30. Now we can write it that way because this one, cosine of 60, is actually equivalent to sine of 30. And so that's how we were able to write using the tangent equation there. If we do a summation of forces in the Y with that way being positive, we get 600, the externally applied load, plus V sine 30 plus N cosine of 30 equals to 0. And again, here I've written this term, N cosine 30. It could have been written as N sine of 60. Now if we put these two together, what we get is 600 plus N tangent of 30 times sine of 30 plus N cosine of 30 equals 0. And if we factor out the N and isolate the 600, we get N times 0.2887 plus 0.8660 equals to minus 600. And let me show you where those terms came from. This number came from the product of the tan 30 times the sine of 30. And the 0.866 comes from right there, the cosine of 30. So that's where those two numbers came from. If we go ahead and solve that, we can figure out what n is. And let me flip to a new page to write that. Turns out that n just equals minus 519.6 newtons. And if we plug that in, we get v equals to minus 300 newtons. Now, let me redraw the diagram and show you why we have those minus signs in there. The diagram goes like this. Okay? And the minus signs mean that the original way that I drew the arrow was not correct. So n is actually pointing this way, and v is actually pointing down that way. And you can see that the x components, the x projections of those two, are equal and opposite. They're in opposite directions. And so if n is negative, that means v has to be negative compared to how I originally drew the arrows. And of course n has to be negative because our 600 Newton force is pointing up like that. There's one more thing I want to say. We're considering these to be centroidal forces, n and v. And so there's no sum of the moments equation that we can really develop here because all the forces are going through the centroid of the section, and that means there's no moment arms for any of these forces. So we don't really have a moment equation in this problem. Okay, now that we've got n and v, let's go ahead and make the average stress calculations. The average stress equations, sigma average equals n over a, tau average equals v over a. So obviously our task here is to figure out what a is. Let me go to a new page and draw another picture where we can figure out what a is going to be. Let me draw a 2D projection of this. Okay. Remember, this angle is 30 degrees. And to figure out the actual area, what we need to do is figure out this length here. I'm going to call it L. Now, the way to do that is to use trigonometry, of course. We know this dimension, which is given back here as a total of 100 millimeters. So this is 100 millimeters. We know that angle is 30. So that means that L cosine of 30 equals 100 millimeters, or L is equal to 115.5 millimeters. We also know that the depth into the page, this direction, is going to be, let's go back to the picture, 50 millimeters. So that means the area is 115.5 times 50. That's 5773.5 millimeters squared. Now I'm going to go ahead and convert that when we write it into meters squared, as you'll see in just a minute. All right, so let's make a sigma average calculation. That's going to be equal to minus 519.6. That was the normal load n. And then I'm going to scale this 0.0057735. Okay, so this thing here is in meters squared, and you can see that there is a factor of 10 to the 6th that shows up in that conversion. This ends up being minus 90 kilopascals. Tau average is going to be equal to minus 300 over that same area, 0.0057735, and that's equal to minus 52 kilopascals. So the only trick here was that we had to calculate the new area. We couldn't just use the cross-sectional area of this rectangle. We had to go ahead and figure out what the length of that inclined section along AA actually was. And once we did that, the calculation was reasonably straightforward. Let's review. We looked at these centroidal loads, N and V, acting along section AA, and we used equilibrium concepts and the method of sections to figure out what those forces are. And we ended up with N equals to minus 519.6 newtons, V is equal to minus 300 newtons. Once we figured out what V and N are, we can go ahead and calculate the average stress. First we calculated the area. based upon the inclined length L, and then we went ahead and made the average stress calculations.